Great. The next talk is over Zoom. It's my pleasure to introduce. Sure. It's my pleasure to introduce Yapeng Tian. Yapeng's starting as an assistant professor at University of Texas at Dallas. I think he just started. Oh yeah. And prior to that, he was a PhD student at the University of Rochester and a master's student at Tsinghua University. During his PhD, he did some really pioneering work on audiovisual scene understanding, including work on audiovisual localization, audiovisual captioning, really covered all the different audiovisual bases. So I'm excited to hear what he has to say.
Okay, can you hear me clearly, Andrew?
Yep, we can hear you.
Oh yeah, great. Thank you, Andrew, for the kind introduction. And I'm very happy to be here and share our recent exploration in human multisensory AI collaboration. It's really a new topic and just start to work on this topic. So first, a very brief self-intro about me. As Andrew mentioned, I recently obtained my PhD from University of Rochester and joined the UT Dallas as an assistant professor in computer science. And I work at the intersection of computer vision, computer audition, the machine learning, and parts of a lot of research focused on audiovisual scene understanding. So which aims to build a unified, explainable and robust multisensory perception systems to understand the spatial, temporal, and multimodal audiovisual content in videos.
Sorry to interrupt
so very recently, I started to collaborate with Professor Toby Lee's HCI group at University Notre Dame.
Sorry to interrupt you, but are you doing a screen share?
Oh, sorry?
Sorry to interrupt you, but are you doing a screen share? We can't see your screen. I don't know if it's on our side or your side. We just don't see your screen. It could be on our side.
Okay, let me share the screen again, and it's kind of weird. Oh, okay. Screen sharing. Can you see the share screen?
I think, can we see it now? I think it's on our side now. So if you just, I think you're good. Just hold on a minute while we get this set up.
Okay.
Great. Yeah, we can see it now.
Okay.
Sorry about that.
Yeah. So as said, very recently I just started to collaborate with Professor Toby Lee's HCI group at the University of Notre Dame to work on building human multisensory AI collaborative systems. So here are our two new works, and Zhengning and Zheng Zhang are the two leading student authors for the two projects. And the first one is an human AI co-creation system for spatial audio generalization. And the second work is the intelligent human AI collaborative tool for audiovisual data annotation. So Zhengning just gave a short introduction about the first work in the workshop. And, so I'm also a beginner in multisensory AI collaboration and not an expert, I would say. In this talk, I would like to share some of my research experience in this area and use our recent work as a proxy. I hope to help you understand the technical challenges in this line for research and also present some research opportunities for you. So before talking about the human parts, so one question you may have is why multisensory AI or audiovisual learning happens. So let's first solve an audiovisual matching puzzle together. So it's very simple, given 4 video frames and 4 sounds, and our goal is to find audiovisual associated pairs. Okay, so let's play the first sound. So the problem is quite easy. So this is the dog sound. We can connect these two. And for the second one, okay, it's a meow sound from a cat. And the third one, so it sounds like a sound pattern from guitar. And for the final one, their rain drizzle sounds. So based on our daily perception experience, we can easily solve the puzzle and find the audio-visual pairs. So the key reason is that sound and sight carry the same semantic information and their natural semantic correspondences between the two different modalities. In a lot of audio and visual data, we can perceive from our daily life. Besides the semantic correspondence, and audiovisual data also have natural temporal synchronization.
Ba, 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 ba.
So in this example, we can see that the lip movements and the speech sound are temporally aligned. And in addition, we may have multi-channel spatial audio, which contains spatial information of sound sources. Let's look at this example. So from this example produced by Pedro, we can see that the overlaid heat map generated from spatial audio can indicate sound source locations for us. So these three different kind of audiovisual data providers widely exist in our audiovisual video data. They enable our audiovisual research, and we have seen many audiovisual research recently. And for example, in audiovisual boosting, various unimodal audio or visual tasks such as speech recognition, action recognition, and sound separation can be boosted by integrating the other modality. And also, learning from sound and sight can enable a range of new applications, such as cross-model generation, self-supervised audiovisual representation learning, audiovisual navigation, audiovisual events localization person, and question answer and dialogue. And using audiovisual learning as a keyword, so we can search in Google Scholar. We can draw this figure, and the x-axis is the data depth, and the y-axis means the paper number. So thanks to several inspiring work developed by our researchers in community, Andrew is definitely a big contributor. So we can see a big increase of this audiovisual research papers since 2017. So each year now we can see new applications and new state-of-the-art multisensory AI models. So compared to human intelligence, so these multisensory AI models, once trained, usually have higher speed of execution to solve the audiovisual tasks. And they're significant in solving the tedious jobs, which are very tedious for human labors. And if high quality audiovisual data is available, and they can also check state-of-the-art performance in fitting the data. But in reality, we only have imperfect data. So with long tail data imbalance open set issue. So for example, for the audio set, which is a larger scale audiovisual data, it's more than 2 million. But there's more than 90% of the data inside the data set only contains speech and music. But there are more than 600 categories. So it's highly long tail, and there's severe data imbalance issue. And also there's certain open set problem in real world deployments. And we usually see significant performance drop for this imperfect data. And in addition, there are essential limits in our current machine learning or multi-model learning tools. So for example, our machine learning model is not capable of solving high-level understanding tasks with reasoning involved. And these disadvantages impact the deployment of these multisensory AI models in a lot of real-world applications. However, we humans are actually good at reasoning, problem solving, and learning. In addition, we have a large HCI research community in computer science. So HCI researchers can design advanced interfaces and provide design guidelines for us, and which can bring humans in. So we can actually incorporate machine automation and human intelligence in a collaborative way to improve our multisensory AI systems and solve our problems. So this is an area called human multisensory AI collaboration. So we aim to design human multi-sensor AI collaborative systems that can integrate machine automation and human intelligence to solve audiovisual tasks better and faster. To build such systems, we can see the core problem we have is how to enable the human AI interaction. For the multi-sensor AI models, we have audio and visual observations, A and V, and then we usually use the deep network to learn a function F to directly predict our desired output. So, but now we have additional human inputs, human intervention. So how to let our humans be able to interact with the function FAV. So now we have additional human inputs can produced by our human users, but now the collaboration can be enabled by human intervention. So here I want to give you some example about the collaboration strategies we probably have. So first one, I name it as early human intervention. So we will have additional human inputs for this function. So the model should be able to jointly learn from audio and visual observations and human inputs. And the second one is the intermediate human intervention. So the human will have to correct intermediate outputs from AI. So we, so for AI models, they are not perfect. They cannot achieve 100% accuracy. Even they can achieve 100% accuracy for the training data and the given testing data, given other new data probably also make some errors. So if we can have a certain intermediate AI outputs and we can have human can validate the results and override the results. And in this way, we can make the AI model better to solve the changing scenarios for us. So the final one is I called let human intervention. So one example is active learning actually. So we can take new human labels to fine tune the AI model to get a improved AI model with the new annotations from users. So today, I want to highlight our two works in this direction and use them as an example to introduce the key components in human multi-sensor AI collaboration. So I will spend more time on the first work and give a very brief overview for the second project. The first work proposed a human AI co-creation system for spatial audio generation. So as introduced, the spatial audio can help us perceive the positions of surrounding sources and improve the immersion of video content. So which is very useful in many application scenarios such as VR and AR, like Alex just talked about. So our community has developed several end-to-end audio visual spatialization methods. This method usually take the mono sound and the associated video frame as inputs, and then use a spatialization network to generate multi-channel spatial audio. So in this example, 2-channel binaural audio is produced. There could be more than 2 channels in the output. For example, in Pedro's work, there's 4-channel first order emisonic sounds are generated from the mono sounds. So although these methods are end-to-end computationally efficient, they usually have limited accuracy, especially for multi-source videos in open domain. And in addition, our user may not be able to understand the results generated by the black box models, and they cannot validate and edit the inaccurate results. And furthermore, it cannot go beyond ground truth. So our AI model generates results which are close to the training ground truth, but sometimes our users may want to create new spatial audio effects. For example, we can move the left piano sound to the right right side and generate a new audio spatial effects. So to solve these kind of issues, we build a human AI collaborative audio spatialization system. Our core idea is to decompose the problem into 2 subtasks. One is object-centric separation, and one is spatialization. And then we build a multi-step AI pipeline to solve the whole problem. And then we use intermediate human intervention to validate the AI results and create new audio effects. So given a raw video and with the mono audio and the video frames here, and we will first use a sound separation model to separate the individual sound sources in the video. And here, two models are used. One is the audio-visual separator developed by me in CVPR 2021, and it's used to separate the music instrument sounds. But beside the music sounds and even speech sound, there's a lot of different ambient sounds. So the other audio-only universal separator, which is used for separating universal sounds, developed by John's group. John's the last speaker of our workshop. He will also talk about audio-visual separation in his talk, I think. So I think that's a very good community to learn more about separation from his talk. So then we can run an audio tagging model to predict some types for each source we have and detect objects in video frames. And then query by the sound type and matching with the visual object type, we can link the detected object with the sound source we have. So then now we have a paired audio separated audio source and the detected objects. So in addition, we run a depth estimation model to obtain the object depth information, combining with the 2D info, so we can obtain the 3D information of the sounding objects. So now, given the video frames, given the audio, we detect the objects and get the 3D coordinates of the object, and also we have the associated, basically the linked audio source, which is separated by the separation model now. So we will have a web stereo audio simulator that takes object 3D information and the separated mono object sound at the inputs to render the spatial audio effect for each visual object we have. And we then can mix the generated individual spatial audio together to produce the spatial audio effect for the whole video we have. So we can see that. So this is the system that can produce a lot of intermediate results. The human can easily understand the intermediate results from these different AI models. For example, we have the separation result, can hear the sound, can learn the separated sound, and we have the predict categories. And we also have the visual object position information. So all this information can be easily understood by our human user, and they can further validate and adjust the results to boost the model performance and even further create new spatial audio effects. So this is the backend model we have in the system. And to enable the human AI collaboration, we need another key component, which is the multisensory interface. Here we design one, it's called Mimosa. So our backend model will first run our audiovisual spatialization pipeline. Then we can obtain the intermediate results and the specialized audio effects. So then we can visualize the intermediate result for each frame. So we have the video frame, we have each detected objects, and we have the separated sound sources. We have sound source categories, and we have the, you can see the different color that can actually synchronize together. And we have yellow one, this is the object, and this synchronized, it's linked sound source we have. And our user actually can move the different dots, which to move the position of the sounding objects, and also they can edit here directly. And we also have a 3D panel. It's visualize the different 3D the objects in the 3D space here. And we can see there are 5 different channels is referring to 5.1 audio type. So here is it's kind of a special audio. There has 5 channels here. The center and the left right for the front and the left right for the back. So we can visualize the intensity of different sound sources. So at first, we will run the interface will run the AI model and to obtain the specialized results. So this is called default spatial audio effects we have. And then furthermore, and then with playing the video and a long time, the user can identify the potential errors we have and then to modify the errors, and the spatial audio will change it accordingly using this system. So for the next, I want to show you one demo to use this Mimosa system.
To illustrate the usage of Mimosa, we demonstrate an example use case where the user already has a video with the binaural audio of a duet band playing in a room. The user wishes to augment the video with immersive spatial audio effects. The user first starts Adobe Premiere Pro and loads the target video clip. From the extension menu, he launches Mimosa. The audio spatialization pipeline will run in the back end. The results of the pipeline will be visualized in the video preview panel in the 3D direct manipulation interface. Using these features, the user can view the predicted sounding objects and make edits if needed. In the video preview panel, several dots of different colors are shown in a 2D overlay on top of the video playback to indicate the inferred positions of the sounding objects. Inferences are inaccurate. The user may directly drag these dots to align them with the actual sounding objects in the video. At the same time, a 3D direct manipulation interface visualizes their positions in a simulated 3D space, allowing users to adjust the positions in a 3D space at a finer granularity. The user can select an output format, and the surround sound with spatial effect will be rendered in real time for preview based on the 3D positions of each sounding object. The sound intensity of each channel will also be visualized to indicate the output of each channel. In addition to predicting the positions of sounding objects for generating realistic spatial audio effects that resemble the ground truth, content creators can also create customized spatial audio effects with Mimosa. For example, the user can adjust the location and orientation of the reference point by directly manipulating the camera icon in the 3D interface. Instead of having the band play in front of the viewer, the content creator may move the viewing point to the back of the band, near the saxophone player, or between the two players. They may also manipulate the positions of sounding objects so that the sound sources can, for example, move around the viewer or out of sight towards the back of the viewer.
So we can see that our user can manipulate the position of the different objects to produce the desired spatial effects for them. So to validate the system, we conduct user study. The users will use the Mimosa system to create spatial effects and evaluate its performance. And two aspects will be evaluated by user. One is the immersion, and another is the realism. So we hope to generate spatial audio, which is not only be able to strengthen the immersion, but also hearing realistic. So 4 videos are compared for each example. So the first RV means the raw video is recorded by it's a recorded spatial audio effects. And DV is a video with default generated spatial audio. And EV here means that it's video with user edited spatial audio effects by our Mimosa system. And the MV means the video with the mono audio effect. So we can see through the study, we can find that the spatial audio effects are generated using the Mimosa pipelines, even in a fully automated way, are more immersive than the mono audio and also the recorded audio. And the user can, user's validation and also the revision in Mimosa can further improve the immersion and the realism of the generated spatial audio effects. And here is kind of like setup of this study. So basically, we can find that the Mimosa system with human in the loop can help us to generate more immersive spatial audio effects. And here are some generated spatial audio effects from our users. So I'm not sure whether it works through Zoom, but if you have a headset, you can hear clearly of these special effects generated by the Mimosa system we have. So in terms of the work, we can identify several key integrates in human multisensory AI collaboration. So first, we should have a multi-step multisensory AI pipeline that produce interpretable intermediate results for us at each of its steps for our user to review, validate, and edit the model results. So if we want to use intermediate human intervention, So for the AI system, it should not be like directly given X and you have FX to have the final result. It should have be certain intermediate results which can be understood by our users, and then they can further validate the results and help you correct the results to make the system better. And then we need an efficient multisensory human user interface that supports human in the loop error discovery and repairment for the audiovisual models. So there are two key components. One is the AI system. It should be able to enable human AI interaction. And second one should be an effective interface that can tag the system and to enable effective human AI interaction. So it's really a co-design. It's not just from either AI side or the human user interface side. So it's really co-designing of this human multisensory AI collaboration system. And finally, going beyond the so-called ground truth. So our human AI collaborative system desire additional content creation ability for authentic users. So for our general AI model, we fit, like given the X, we have learned FX fit to the Y we have. But sometimes for our user, they probably want to do very crazy and creative editing creation for them. So it's for this kind of system we design, we should be also consider this kind of factor to enable the content creation for certain users we may have. And similar rules can be applied in our second work. In the work, we try to develop an intelligent human AI collaborative tool for audiovisual data annotation. So given the video frames and the audio clip, we want to annotate the sounding objects and their and also their categories in each video frame we have. So the annotation system is AI powered. We use audio and visual analysis models to produce the candidates for our human users, and it can reduce a lot of tedious human perception and labor and efforts. But you know, there's AI model, it could be something wrong here. So our human users can further validate and edit the result to ensure the annotation quality. So basically, the AI models will be further updated in terms of the human intervention. After we have the new edited results, we can further use the system to update the results. For example, we can automatically change the annotation in neighboring frames according to the camera smoothing, and also the produce the results from the user, and also the AI generated result, combine them and using smooth method to avoid the manual frame by frame editing. It's very tedious if we would do, like for each frame we correct the results. For the neighboring frame, it's possible that we have the similar error. So basically, we can have more efficient algorithm can help us to avoid the frame by frame process to obtain the audiovisual annotation. And besides about two works, human multisensory AI collaborative system is also applied to produce accessible videos for blind and visually impaired users. So blind users watch videos only use the hearing. They cannot really see the content as we can normally watch video. But there are some video content that can only be seen, but which are not audible. So the visible only visual information is not accessible for our blind users. So to make content more accessible, people usually use the audio description as shown here, and overlay the audio description speech with the original audio track to generate a new video. And in this way, the audio description can tell what's really happening in a visual side, and which cannot be heard by the blind users. And in this recent WIST paper, the system automates the audio description creation process with audio-visual learning models. So it uses audio-visual embeddings to have measure the audio and the visual correspondence and identify the non-accessible content for users. So basically, this is the first model is the audio-visual model, and developed by our committee, and the second is the visual text model. It's for for the audio content in the video. There's speech content and the non-speech content. So for the speech content, that will use the visual text model. Basically, this model to help us to generate certain measurement score to tell us whether it's a match or mismatch. And if there's non-speech, we have a general audio-visual embedding. So we have a lot of self-supervised learning methods that can help us to produce very powerful representations for the two different modalities, and it can also generate a score. So basically, you can combine the speech and non-speech score and to identify where's a certain segments, there's a visual content that they're not synchronized with the corresponding audio content. And then there's human users, they can see, identify the content, and they can validate whether it's a true non-accessible segment, and then the users can decide whether pick or not, and to write the description to describe the content they have. And finally, that generates the audio description video track, and to have a more accessible video for the blind users. And this work also won the best paper award. And here are some take-home messages. So, this very short talk here is not possible to cover lots of components inside, but here I just want to give you a very brief intro about this human multisensory collaboration field, and help you get some ideas, know the certain challenges, and understand certain potential open opportunities we can take. So first take-home message is human multisensory AI collaboration indeed can help us to make our system better. And to enable the human multisensory AI collaboration, there are changes for both sides. So for the AI side, so how to enable the collaboration and incorporate the human intervention in our computation pipeline. And for the human side, how to design an efficient and effective interface to facilitate discovering and repairing errors and creating new content for users. And there are many research opportunities for us in the future. It will be exciting to see new works in incorporating machine automation and human intelligence to improve learning infrastructure, to building more efficient audiovisual data collections interface, and to promote accessibility to generate more accessible content for all the human users, and also strengthen machine capability for us, and the potential other applications we can explore in the future. And that's all I have today, and I hope this short talk can help you to have a very brief idea about this interdisciplinary research area, and thank you for listening, and I'm happy to take any questions you have.
Does anyone in person have questions for Yapeng? For those who are remote, you can type them into the chat. So I have a question about the Mimosa system.
Yeah, sure.
If the audiovisual localization method fails, if it thinks the sound is somewhere else, can you still fix it? Or how reliant are you?
So, yeah, this is a really good question. So you can see for this audio spectralization system, it's very important to associate the audio with the corresponding sounding objects we have. So basically, there are certain times we have the inaccurate detection result to obtain the wrong visual objects, and we potentially also will have the wrong category prediction to we cannot directly use them to link the two different components from audio and visual side. So basically, here our human user can come, so they can review the results, and they can listen to the sound, they can see the video, and then they can look at the detected objects that are kind of different dots there. If there's something wrong, our human user can draw the different dots and to move around to let it go to the correct prediction for the different sound sources. So in this way, we can fix the wrong predictions in the sounding object localization we have.
Thanks. Any questions? Okay, I have one more. In the second system that you described, how does the sound factor into the location of the bounding boxes? It sounds like a human in the loop has to select those bounding boxes. How much do they actually use audio for that?
Okay, so it's very it's kind of also, it's a joint audiovisual analysis system in the AI loop. So it's a visual.
I'm sorry, can you?
We have multiple different audio frames, the visual frames, and for the audio, it's kind of a clip. It can cover multiple different frames, and for the audio, it's visual consistency. It's one way, to kind of speed up.
I'm sorry. Can you
whole,
repeat this?
like,
We just
animation
you
to
unfortunately
decide
you're
a bunch of different video frames which can actually have a consistent audiovisual content. We can directly like go through this kind of bench and speed up the whole process. So it's really first, the audio come here is two parts. One is associated with the audio with the visual objects detected, and second, the audio. It's like a real hands action recognition paper before. It's audio. It's kind of speed up and to make it more efficient action detection, action recognition model. So here is audio is used here to as a signal to help us to do more efficient annotation, something object annotation for us.
Thanks. Yeah, I missed the beginning of your answer, but I think I got it from the end. All right, let's thank Yapeng again.
Okay, thank you so much.